Hi everyone, I'm Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Methods of biasing circuits, part 2. So, overview of today's presentation starts with introduction. So, different methods of biasing. So, mainly we focus on collector to base bias or collector to feedback bias, collector to emitter feedback bias, and voltage divider bias or self bias device or emitter bias, and conclude with summary. So coming to the introduction, biasing is the process of adding external DC voltage to the diode, forward bias and reverse bias. So it is the setting of DC operating conditions of an electronic component that process the time varying signals, example BJT, FET, MOSFET. So it is an essential to maintain proper operating point or Q point. So consider CE configuration. So you will have Q point VCE comma IC. Collector to emitter voltage and collector current must be maintained properly. So we have these are the different methods. In the previous session we have discussed first two. So today we mainly focus on these three: collector to feedback bias, or we can also call it as collector to base bias, and then collector to emitter feedback bias, voltage divider bias or self bias or emitter bias, or we can sometimes call it voltage follower also. So let us see collector to base bias or collector feedback bias. So this is the circuit. So here there is a resistor between collector and base. So this gives the name collector to base bias. Here the voltage drop across RC increases due to temperature effect. So because in the IC increases, a larger value of beta also increases, of course. So these are the main reasons why voltage drop across collector resistor is increased. So if you use the transistor with having a more beta value, amplification factor, then also there is a change, voltage drop across collector resistor RC. And another important reason is change in the collector current. So thereby reducing the value of VCE. Therefore, IB decreases, which in turn compensates for the increase in the IC. So thus, greater stability is obtained. So this is another advantage of using collector to base bias. So if you apply loop equation in the first case, so we have VCC here, IB plus RC into IB plus IC into RC, IBRB, and then plus VB. So VB is already given here, and from this we can simplify to get the IB expression. So base current expression, from this equation we can write VCC minus VBE minus ICRC. So here we can combine IB and IB. So if you combine this, so you will get RC plus RB. So however IB is here, so IB is equals to VCC minus VBE minus ICRC by RC plus RB. So and then now as usual, so differentiate this IB with respect to collector current IC, then you will get RC by RC plus RB. Now if you substitute in this expression, stability factor expression, then we will get 1 plus beta by 1 plus beta into RC by RC plus RB. Here one important point here we have to be note that if RC is very small, here this RC is very small, then S is equal to 1 plus beta, the stability is very poor. So that means the stability factor depends on collector resistor here. So hence the value of RC must be quite large for good stabilization. It is not satisfactory for circuits like transformer coupled amplifiers. So this kind of stability factor, this kind of biasing circuit does not suit for transformer coupled amplifiers. So where DC load resistance in the collector circuit is very, very small. So that's why we cannot use this kind of collector to base bias circuits for biasing purpose in case of transformer coupled amplifiers where DC load line resistance in the collector circuit is very small, right? So this is about a collector to base bias. Similarly, we have another one, collector to emitter feedback bias. So this is the circuit for this collector to emitter. So collector to emitter means here again we have added emitter included, and here collector to base we have RB is there. So both collector to collector feedback and emitter feedback. So we have introduced collector feedback and emitter feedback. Here collector to feedback is provided by connecting a resistance, series resistance or RB from the collector to the base, and emitter feedback is provided by connecting emitter resistance RE from the emitter to the ground like this. So these two setup will be given for the biasing purpose. Both feedbacks are used to control collector current IC. So these feedbacks are used to control this IC, output current IC. Therefore, and the base current IB in the opposite direction to increase the stability as compared to the previous biasing circuits. So when we compare to the previous biasing circuits, so this is suitable because here we have a stability factor is reduced. Apply KVL in this circuit, you will get a IB plus IC into RE. So because this IB plus IC current will flow up to resistor RE. So therefore you will have IB plus IC into RE and VBE, IBRB and IB plus IC into RC minus VCC. So this is the expression for KVL. After applying KVL, you will get this expression. So from this, let us simplify to get the IB expression. So IB expression can be written as VCC minus VBE by RE plus RC plus RP and minus RE plus RC by RE plus RC into IC. So therefore, let us differentiate this with respect to IC, collector current IC. So that is minus RE plus RC, RE plus RC plus RP. So here this is your DIB by DIC. Now let us substitute in the stability factor expression. 1 plus beta by 1 minus beta into DIB by DIC. So what is the DIB by DIC? This one. So 1 plus beta RE plus RC by RE plus RC plus RB. Now the stability of the collector to emitter feedback bias circuit is always better than the collector feedback and emitter feedback. The previous circuits, the biasing circuits compared with the previous biasing circuits, this collector to emitter feedback bias gives more stability factor. So that is the one of the important advantages of this kind of biasing circuit. The last one is voltage divider bias, self bias or emitter follower, you can say potential divider circuit. So here we have to use this kind of biasing circuits. Voltage divider bias used for low collector resistance. If the collector resistance is low, then of the order of 100 ohms. So we can say we can use this kind of voltage divider bias or self bias. Here the current in the emitter resistor RE causes a voltage drop which is in the direction to reverse bias the emitter junction. So after using this RE, here it causes voltage drop which is in the direction reverse bias the emitter junction. So because of this, the emitter junction will be reverse bias. Now the required base bias is obtained from the power supply. So for the base bias, this voltage can be used. Potential divider network of the resistance R1 and R2. So therefore, the required base bias is obtained from power supply VCC through the potential divider network of the resistance R1 and R2. So here the potential divider network provided by this R1, R2 and RG here. So therefore, use of self bias circuit as a constant current circuit. So this is very important. It is mostly used biasing circuit. Here, if IC tends to increase, say due to an increase in the IC naught. So IC naught means reverse saturation current. When it is increases with temperature. So usually when temperature increases, the minority charge carrier concentration increases. So IC naught increases, which in turn IC also increases. The current in RE increases. So when current in RE increases means drop will be more. Hence, the voltage drop across RE increases, thereby decreasing the base current. So as a result, IC is maintained almost constant. So if base resistance is reduced, so IC almost maintained constant. So, and to solve this, we have to use some Thevenin equivalent circuit. So this is the Thevenin equivalent circuits of this. So here R1, R2 and IB. So can be written as in terms of RB. So, and which is replaced with a input voltage source VT, Thevenin voltage. And here now you can simplify this. So here Thevenin's voltage given by opposite voltage by total opposite. This is opposite resistance R2, right? So if you want to know the voltage Thevenin equivalent, this is the VT. So if you want to know this, so we have to use opposite resistance by total resistance into input voltage. What is input voltage here? VCC. So R2 by R1 plus R2 into VCC. And RB is R1 R2 parallel combination. R1 R2 by R1 plus R2, because this is parallel combination. And then now VT is equals to IB RB plus VBE plus IB plus IC into RA. And now, so from this we can get the IB value. So after getting IB expression, we can apply this differentiation with respect to collector current IC. DIB by DIC is equals to minus RE by RE plus RB. So therefore, S is equals to 1 plus beta by 1 plus beta into RE by RE plus R2. Now if you substitute, the value will be 1 plus beta into 1 plus RB by RE by 1 plus beta plus RB by RA. So that means here the stability factor is very less compared to remaining. The value of S is equal to 1 if the ratio of RB by RE is very small. So it is depending on the emitter resistance and as well as base resistance. So if ratio of RB and RE is very small as compared to 1, so of the order of 0.1, 0.3, then your stability factor value equals to 1. So this is the best, this kind of circuits gives best stability factor S, right? So let us conclude. We have discussed introducing the biasing methods. So we have already discussed fixed bias and emitter bias, and previous video you can search for these two topics, fixed bias, emitter bias. So today we have covered collector to base bias and collector to emitter feedback bias, voltage divider bias or self bias device, or emitter bias. And probably the next topic will be BJT applications. Let us start. Thank you.